Okay, so we've got the definition of the centre of a group, which is things that commute past all elements of the group. The group I'm going to consider is the group of 2 by 2 matrices with non-zero determinant under regular matrix multiplication. Matrix mult. Under matrix multiplication. So my matrices are going to be A, B, C, D. All these guys are real numbers here, with A, D minus B, C, which is the determinant, not equal to 0. And the reason I specified that the determinant is not equal to 0 is that I want these guys to be invertible here. So what's the centre of this group? Well, we'd better make sure that the matrix A, B, C, D commutes past everything. And so what I'm going to do, I'm going to multiply on the right by this very simple matrix here and see what we get. I'll fill in the entries in a minute. And then I'm going to multiply it on that side by that. And we'll see what condition we need to, we'll see what condition we need to put on A, B and C and D to make these two guys equal. If you're worried about the fact that this matrix here isn't actually in the group because it's got a 0 determinant, that's a very good observation. You've got to consider I2, which is equal to 1, 0, 0, 1, plus this matrix here, and then do the analysis with that matrix there, and then subtract off the identity. But I'm not going to worry about that. Okay, so what's the top one? A, B, C, D. So it's going to be A. Top right is going to be 0. That's going to be C. That's going to be 0. Now this one. That's A. Top right is going to be B. 0, 0. So what does that tell us? That tells us, well, because these two matrices have got to be the same, this is the condition, of course, for A, B, C, D being in the centre. So if this matrix here, A, B, C, D, is in the centre, these two guys here on the right are going to be equal. So that tells me that C equals 0. That's a good start, because this element here is 0 here, so it's got to be 0 here. A equals A, well, that's no help. And also B equals 0. So straight away, we've got C equals B equals 0. So we've got A, 0, 0, D, diagonal. Diagonal. There we go. Must be a diagonal matrix. Is there anything else we can say? Well, we can try a different matrix. Let's try putting the 1 over there and see what happens. A, B, C, D times, I'm going to put the 1 on, oops, I'm going to put the 1, see it's top left here, I'm going to put it top right. Okay, so that's a 0, that's an A, that's a 0, and that's a C. Let's do it the other way around. 0, 1, 0, 0 times A, B, C, D equals blah, 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 blah. Notice that when I'm doing this, all I'm doing is writing down the definition of being in the centre, and I'm just mucking about with it. I'm not doing anything clever here. That's C, that's D, 0, 0. So by matching the top right position, I know that A equals D. And I also know from this one that C equals 0, but we knew that anyway from up here. So A equals D. So we've got this format here, and we've got A, 0, 0, D, and now we know, we had this from above, and now we know that A equals D. So that tells me that we've got matrices of the form A, 0, 0, A, which equals a constant, a constant scalar times 0, 1. No, it isn't. It's 1, 0, 0, 1. There we go. So it's constant times I2, the identity matrix of size 2 by 2. And indeed, if we consider n by n matrices under regular matrix multiplication, matrix mult, then we get the centre of this by very, very similar arguments, slightly more technical because you need to keep track of rows and columns and stuff. The centre is basically a constant times I n, the identity matrix of n rows and n columns, which is quite an interesting observation. The point I want to make about this is that the centre here is a very restricted, it's a very small subset. If you have a great big matrix with lots and lots of entries, loads and loads of degrees of freedom here, great big matrix, loads, could be thousands by thousands, huge, great big matrices, a great big space. The centre of that space is just of this form. It's got the same number all the way on the diagonal and then zeros off it. This is a very small subset, or a very small subspace, I guess, of the full space of matrices. Very small space indeed. And so what that tells you is that the centre is small in some sense. And so that tells me that matrix multiplication is very unabelian. And I don't think that's a real word, but yeah. It's very unabelian. What that tells me is that matrix multiplication, you all know from elementary maths that AB is not equal to BA in general. It's not only not equal, it's sort of very not equal. I'm not explaining this very well. What I mean to say is that matrices which do commute past each other are rare. Well, that's just the same thing as saying that the centre's small, really. That's the same thing as saying that the centre's small, almost. Okay, so I'm going to stop there. That's a nice little observation.